Alright, silly people, here's the situation. I just woke up, I'm still drinking my coffee, and I felt like doing some linear algebra, so let's get into it. Did you know that the exponential of a matrix can be expanded as the Taylor expansion of the exponential, using the same formula as you would for any other exponential, just having matrices as the arguments? Let's do this for a couple of examples, shall we? Uh, the first example being the matrix 0, 0, 0, 1, 0, 0, 3, 4, 0. This is going to be a nice one to do it on because it's going to turn out that you can't multiply this matrix by itself very many times. What's up, Gimli? Let's just put you down. I can multiply this matrix by itself a couple of times. So m squared is looking like I can tell you that the bottom row is all zeros and the first column is all zeros because that's what the original matrix looks like. But then 0, 1, 3, this is 0, and also 0 here. And then this is actually 4, right? But then this is 0. So m squared is 0, 0. It's a bunch of zeros with a 4 in the top right corner. If you multiply this by the matrix again, definitely getting zeros in the first two columns and also the bottom rows and also at the top right corner. So yeah, the matrix doesn't go up to third order, it just goes to second order. So the exponential of this matrix will just look like the identity matrix plus the original matrix 0, 0, 0, 1, 0, 0, 3, 4, 0, plus 1/2 of m squared, which is 0, 0, 0, 0, 0, 0, 2, 0, 0, which is, if you add all those guys up, then you get 1, 1, 1 from the identity element, but then also 1 here from the original matrix. 2 plus 3 makes 5, so 5 here, but then 4 here from the original matrix, and the rest is zeros. Right, that's kind of funky, that the exponential of that matrix gives you that. The next matrix we're going to try this on is the matrix formed by m equals 0 minus theta, theta 0, which is cool. And even it will behoove us to write it like this sometimes. Theta times 0 minus 1, 1, 0. My quantum field theory friends will recognize this as gamma 0 in the Weyl representation. But yeah, if you square this guy, then you're going to get theta squared times 1 minus 1, or actually theta squared times 0 minus 1, 1, 0 times itself. And I wanted to show those matrices next to each other explicitly, because you get 0, 1, this is going to be minus 1, 0 here, and then 0, and also minus 1 here. So it's minus theta squared times the identity element, or just minus theta squared if you're feeling lazy like I am. So that's kind of crazy. Let's take this up to the next order up, m cubed. It will be, m squared times m. So it's minus theta squared times 0 minus 1, 1, 0. Theta cubed even times that. And, why even expand further? That's what it looks like. And I even want to take it to the next Taylor expansion so you can see the next term explicitly, but it is just m squared times theta, and it's equal to theta to the fourth times the identity element. So it looks like the Taylor expansion of this guy is the identity element plus 1/2 of theta squared, so actually minus 1/2 of theta squared times the identity element, plus, this is also minus theta cubed over 3 factorial times the original matrix, this guy, and then the fourth element is theta to the fourth over 4 factorial. So the odd terms and the even terms seem to have a particular pattern to them, right? So let's write the even terms and odd terms in terms of their own series representations, shall we? So plus, and this is where I'm going to stick the even reps, the even powers of the expansion, n equals 1 because we're starting with, theta squared, to infinity though, and it seems to have a minus 1 to the n. It's flipping signs all the time, or actually it's minus 1 to the 2n, I think. No, that doesn't make any sense because that would just be 1 to the n. So it's definitely minus 1 to the n. Get out of here, dude. And then also, it seems to have a theta to the 2n on it, right, to take care of the power of 2, but it's also multiplied by 2, or divided by 2n factorial. So that you can get 2 over here and 4 over here. Yeah, okay. And then the odd terms, the ones that are multiplied by the weird matrix, so I'm going to stick the weird matrix here actually, 1 minus 1, 0, are in a sum. It's actually a sum of starting with n equals 0 now, because the first, oh, I forgot to write the linear term in the expansion. I should do that. Just for completeness purposes, there is a term linear to the, oh, come on now. Give me that brace. Give me that parentheses. What are we doing here? This is the content that you came for, by the way. This is exactly what you should expect from me at this point in the day. But yeah, this first term is linear to theta times 0, 1, minus 1, 0. Right, okay. This one starts with n equals 0, because it's going to be to the power of theta times to the 2n plus 1, right? And then it seems to have minus signs on every other term, so this is going to be a minus 1 to the n as well, I think. Yeah. And then it's divided by 2n plus 1 factorial, right? Because it's divided by 1 factorial or 0 factorial. No, it's divided by 1 factorial for the first element, and then 3 factorial for the next. So 2n plus 1 factorial. This step would be really cool if the identity matrix was already included in this sum, but we can make it included in that sum anyway if we just start at n equals 0 instead of n equals infinity, right? Because it'll be theta to the 0. Yeah, it's the same thing. So we can instead write the sum now with it, sum from n equals 0 to infinity of this junk over here, but then also times or plus this stuff over here that's multiplied by the weird matrix that we started with, right? My cat keeps invading the video. Yeah. So, but this is cool because this is just the Taylor expansion of cosine theta now. And this is the Taylor expansion of sine theta, which means we can write this as cosine theta, which is cosine theta times the identity element, but also sine theta here and minus sine theta here. So it's the rotation matrix. Isn't that crazy? And that's why a lot of like quantum mechanics books just say that e to the theta is the rotation matrix. Kind of weird. But let's keep going. If my cat would get off my textbook, I could read the next part. It's looking like show that that M is diagonalizable. If M is diagonalizable, then the determinant of M is equal to the trace of M. That's a crazy thing to say. So I think the place to start with this one is, that if M is diagonalizable, then you can write S being some unitary matrix which transforms M to its diagonal form like this, right? So that is true. What if we write instead S e to the M S inverse? Then, that should be equal to e to the d, right? But we'll actually evaluate what it looks like, because e to the m, we know, is a Taylor series expansion of m. So it's 1 plus m plus m squared over 2 factorial plus m cubed over 3 factorial dot dot dot. And that's times S inverse. Let's let the S inverse S move into the parentheses now. So you get S inverse plus S inverse plus 1 over 2 factorial S inverse plus S inverse over 3 factorial and on into infinity. The way that I wrote the squared term and the cubed term like that is because when we set this equal to 1, this equal to d, and then this equal to, you can insert S inverse S in between the m's, because S inverse S is equal to 1, yeah. So this is going to be S inverse S inverse plus S inverse M, and there needs to be another S in there, S inverse inverse 1 over 3 factorial plus dot dot dot. Well, what is S inverse? It's always d, so this is d squared, and this is 1 over 3 factorial times d cubed, which means that, S inverse is equal to e to the d. So that's kind of crazy. What if we take the determinant of this equation now? Just for fun. The determinant of S inverse is equal to the determinant of e to the d. Well, determinants split up multiplicatively. So this is the determinant of S times the determinant of e to the m times the determinant of S minus 1. Right? And then on the right-hand side, it's the determinant of e to the d. I'm not going to expand it right now. S is a unitary matrix, which means its determinant is equal to 1. So we can also just write this as the determinant of e to the m on the left-hand side, and on the right-hand side it'll still be the determinant of e to the d, which we haven't expanded yet. But you can see that we're almost there on the proof. We just have to expand determinant of e to the d now. So that e to the d is looking like the determinant of 1 plus d plus, d squared over 2 factorial plus d cubed over 3 factorial, and on into infinity, right? What does d actually look like in its structure? D is the matrix of all of the diagonal elements of M, right? So if it's equal to the eigenvalues of M, right? So if M has eigenvalues lambda 1, lambda 2, dot 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 on into infinity. And that's how you would write d. D squared then would be very simply lambda 1 squared, lambda 2 squared, dot 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 on into infinity. So the determinant of e to the d is the determinant of 1 plus, and then in parentheses, lambda 1, lambda 2, dot dot dot, plus 1 over 2 factorial, lambda 1 squared, lambda 2 squared, dot dot dot, and then let's just say on into infinity at that point because I'm running out of space on this line. So that's equal to the determinant of, if you add together all of the matrices, 1 plus lambda 1 plus 1 over 2 factorial lambda 1 squared plus dot 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 on the first element, and the second element will be 1 plus lambda 2 plus 1 over 2 factorial lambda 2 squared plus dot dot dot, and then dot 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 for however many eigenvalues m has. And look at that. Each element of the matrix turns out to be a Taylor expansion of the eigenvalue that it represents. So it's the determinant of e to the lambda 1, e to the lambda 2 for the second element, and on into however many e to the eigenvalues you want. And then that determinant turns out to be just, you multiply all the diagonal elements together, it's e to the lambda 1, e to the lambda 2, e to the lambda 3, dot dot dot, which means because exponentials work the way that they do, you can write this as lambda 1 plus lambda 2 plus lambda 3 on infinitum, which is actually just the trace of m, right? Because for diagonalizable matrices, the trace of the original matrix is equal to the trace of its diagonalized form. So that is equal to the trace of m. And remember, we started at the point where this is the right-hand side to the equation. Determinant of e to the m is equal to this. So determinant of e to the m is equal to the trace, or e to the trace of m. Isn't that nice? Gimli keeps sitting on my textbook, so I don't know what the next part of the problem is. Show that if the matrices m and n commute, that e to the m plus n is equal to e to the m, e to the n. This is a part of the problem that I don't fully understand because it's really weird. But basically, if you expand e to the m plus n as a Taylor expansion, you see that it's 1 over, or actually it's a infinite sum, right? And I'm just going to write this the series representation of the sum now instead of writing all of the bits. It's 1 over n factorial times m plus n to the n. There is a old formula called the binomial theorem that I think even Newton worked on a little bit, where if you take m plus n to the n, then you get an infinite sum over m of a binomial coefficient, which is n m, times the first matrix to the n, so m to the n, times the second matrix to the n minus m, right? It's an absolute classic mathematically. And so what does the binomial coefficient actually look like? I think that's a thing worth expanding out, because it is n factorial over m factorial times n minus m factorial on the bottom, and this is still m to the n and n to the n minus m. This n factorial that we had from the Taylor expansion cancels out this factorial that was in the binomial theorem. So we have a couple of sums, and also might I just say that the sum uh, over m is not actually infinite. It only goes to n, whatever level of n that you're on. That's how far m goes. That was just a little hiccup on my part. But yeah, it goes to n, and then the thing is m factorial over n minus m factorial. And then it's m to the n minus m. And you see why I would think that that looks like two little Taylor expansions right next to each other, right? That's not even that big of a stretch. But I think what Griffiths did to prove this problem is that if you change the order of the sum, you sum over m first and then n first, rather than n first and then m first, which is only something that you can do if the matrices commute. If you can change the order of the matrices, then you can change the order of the sum. And then he drew this little figure that I don't really understand. But basically, you can redefine a variable k as n minus m, and then you can rewrite the Taylor expansion as two infinite sums rather than one infinite and one finite. And only because the matrices commute can you do that. This is now going to be a sum of k equals 0 to infinity of 1 over, it's going to be n factorial times k factorial, m to the n to the k, which means it's a couple of exponential Taylor expansions. So that's e to the m times e to the n, which is what we were trying to prove in the first place, that this is equal to that. So yeah, if you weren't satisfied with that proof, maybe just go read somebody else's proof of it, because I don't really understand it. But also, he wants us to prove explicitly that this doesn't work for matrices that do not commute with the simplest possible matrix that we can think of. So what if we choose m equals 0, minus 1, 0, 0, and n equals 0, 0, 1, 0. Why is it useful to choose this matrix in particular? Well, that's because m plus n is equal to 0, minus 1, 1, 0, right? Which is a matrix that we've already dealt with. This is the theta matrix again, if it was multiplied by theta. But e to the m plus n at that point is equal to sine, or actually it's cosine of the diagonal element, so cosine of 1 minus sine of 1, sine of 1, cosine of 1. That's going to be the left-hand side of the equation. What about the right-hand side if we do e to the m times e to the n? Well, it's going to be the Taylor expansion of 1 plus m plus m squared over 2 factorial plus dot 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 times 1 plus n plus 1 over 2 factorial n squared plus dot dot dot. So we better find what m squared and n squared are. M squared is going to look like just multiplying the matrix by itself. 0 here, and then 0 here for sure. And then, yeah, the right hand is just zeros. So m squared is 0. I think you'll even find that n squared is probably 0. Yeah, it looks good. So n squared is actually 0, and m squared is actually 0. So e to the m, e to the n is equal to 1 plus m times 1 plus n, and it doesn't go to higher orders. So it's actually just 1, 1, 0, minus 1 times 1, 1, 1, 0 here. Multiply those guys together. You get 1 on the diagonal. You get a 1 here. Bam, bam. you get a -1 here, and then yeah, it's just a -1 there, pretty sure. And this is a -1 plus a 1, so 0 here. Well, I can tell you it's definitely not equal to sines of 1s and cosines of 1s. That is to be sure. I can be sure about that, which means this is not true for matrices that don't commute in general. Okay, Gimli's out of my textbook again, so let me... Oh, this guy. He loves sitting on my textbook. If M is Hermitian, show that e to the IH, or if H is Hermitian, show that e to the IH is unitary. So he's saying if you have a matrix H which is equal to its own Hermitian adjoint, then e to the IH times the Hermitian adjoint of e to the IH is equal to 1. So let's just evaluate these, shall we, and see if it goes to 1. Well, we can just do the Taylor expansion of e to the IH inside the dagger anyway, because I don't really care about the first term, it turns out. It's going to be the dagger of 1 plus IH minus H squared over 2 factorial minus IH cubed over 3 factorial and on infinitum, and then you take the dagger of that. Well, if you move the dagger inside, the dagger of 1 is 1. The I will get a minus sign on the first term. The second term is the same, and then the cubic term also gets a minus sign, so this is plus IH cubed over 3 factorial. And also, all of the h's have daggers, but because h is Hermitian, all of those daggers will just go away. So it looks just like h on each of them, right? Which means this is also just equivalent to the Taylor series expansion of e to the minus IH, if you think about it. And then exponentials work the way that they do, these terms will cancel out. So this is equal to 1, as it turns out. So this is a good proof, I think. All right.